Hello and welcome to our second lectures in statistics and probability. Last lecture we talked about probability models and Venn diagrams. A quick recap. Probability models, they are made of a sample space with all of the events of that model that we are studying, the events themselves of course, and probability measures that tell us how likely an event is to happen. The probability measures, they came with a couple of properties, if you remember. The fourth property is the one that we'll be focusing on today, is the property of additivity, stating that if two events are disjoint, meaning they don't overlap together, then the probability of one event or the other event happening is equal to the sum of the probability of each one of these events, right? So let me just write that here again. If you remember with a Venn diagram, if I have a Venn diagram here, for example, and I have the event A and the event B, you can see they are disjoint. They don't overlap. And because they are disjoint, then the probability of event A or the event B, this means union, which is equal to OR, as we saw on the previous lecture, would be equal to the probability of A happening plus the probability of B happening, right? And this is something important for what we'll be talking about today. Knowing this additivity property, we can come with a couple of other properties of probability models, some insights of how they work, things that will be useful to characterize or to study models when they become a little bit more complex than what we've been talking about up to now. The first insight that we can have is the following. Let's consider this Venn diagram that I'll draw here. If I have the sample space S with an event A inside of it, and this is our sample space S, anything outside of A, as we mentioned on the last lecture, is A complement. So the probability of A complement is equal to the probability that A does not happen. Now observe here that A and A complement, they are disjoint. They don't overlap. You can't have A not happening and A happening at the same time. Now because they are disjoint, then the probability of either A happening or A complement happening is equal to the sample space S, the probability of S, which is equal to 1. Right? We saw in the previous lecture that the probability of anything happening is equal to 1. And here, our event A plus the event of A not happening is equal to anything happening, S. And from this then, we can derive the following. The probability of A or A complement is equal to the probability of A plus the probability of A complement, which is equal to 1. So the probability of A complement, the probability of A not happening, is equal to the probability of A happening. Sorry, let's do that again. The probability is equal to 1, the probability of anything happening, minus the probability of A. And this is a great insight when it comes to more complex probability models. Right here it seems kind of arbitrary, it seems obvious, but it's very useful to write and say these things in mathematical language, such as what we just did here, so that we can know how to use them in the future when working with more complex things. So this is the first insight that we got from probability models. Let's look now into something that we call the law of total probability. So the law of total probability. Consider this case here. If I have a sample space, let's do this in gray. If I have the sample space S, and this sample space S is divided into subsections that I will be calling A1, A2, A3, etc., all the way to A something that we'll call AI. Say it was divided in 6 pieces, then AI would be A6, but it can be divided into any number of events. And notice that A1, A2, A3, all of these, they don't overlap, so they are disjoint, right? They are disjoint. Now consider that there is an event B there will be this green circle. This is the event B that overlaps with all of these disjoint events that are dividing our sample space S. So all of these events, A1, A2, A3, all the way to AI, they are dividing S. So the sum of A1, A2, A3, etc. is equal to S, right? Now, what is the probability of B? The total law, or the law of total probability, states that the probability of B will be equal to the probability of A1 intersect B plus the probability of A2 intersect B plus all the way to the probability of AI intersect B. And it may sound kind of complicated, but we can have a very easy way to understand how this works just by looking at the Venn diagram. Let's look at the Venn diagram here. I am saying that the probability of this green circle, anything on this green circle to happen, is equal to the probability of this piece of the circle. This piece of the circle, let's move this guy away. So this piece of the circle here, this is the intersection between A1 and B that we write like this. A1 intersect B. Then we also have this guy over here. Let's choose blue. This guy over here is the intersection between A2 and B. Again, then we have this other guy over here. And this guy over here is the intersection between A3 and B. And you can go all the way like this to AI. Now notice that these intersections, A1 intersection B or A2 intersection B, they don't overlap. They are disjoint, right? So because they are disjoint, by the principle of additivity that we mentioned previously, we can say that the sum of all of these guys will be the probability of B, right? So the probability of B is all of the green area here. So the probability of B is equal to the probability of A1 intersect B plus, let's use some more colors, right? Is equal to the probability of A1 intersect B plus the probability of A2 intersect B plus the probability of A3 intersect B plus all the way to the probability of AI intersect B. And this is what we call the law of total probability. Okay. Now let's suppose the following Venn diagram. Let's consider the following Venn diagram. If I have the sample space S, inside of my sample space I have A, and inside of A I have B. So B is a subset of the event A. This we would write A contains B. This is how we write it in mathematical language. A contains B. If this is the case, if A is containing B, then I can say that the probability of A is equal to the probability of B minus or plus the probability of A that intersects with B complement. Again, B complement is anything that is outside of B, right? So the probability of B complement, so B complement here in our Venn diagram will be anything outside of this B. So here is our B. Everything outside of the B is B complement. But I want the probability of A. When I say the probability of A intersect B complement, what I'm referring to in this Venn diagram is this section of A. All of this outside of B, but that is inside of A. This is the probability of A intersect B complement. So the probability of A, the whole circle, including B, we need to have this A complement B, A intersect B complement, plus the probability of B, right? So then the probability of A is equal to the probability of B plus the probability of A intersect B complement. And at the same time, from this equation, we can then derive that the probability of A intersect B complement is equal to the probability of A minus the probability of B. I'm just rearranging things here. So this guy goes over here, this guy goes over here with a minus sign. Okay, great. So we talked about events that are disjoint. We talked about events that are inside of each other. What about events that are not entirely inside of each other, but that still overlap, still intersect? I have a general term then that will allow us to calculate the probability for the union of any events, even if they are not disjoint or if they are disjoint, it doesn't matter. We have this general term to calculate the union of any events, and that will be the probability of A union the probability of B is equal to the probability of A plus the probability of B minus the probability of A intersect B. Wow, Matheus, where did you come up with this formula? How do we find this? Because right now it seems to come from nowhere, but we can have, there is a very precise proof for this, but I won't be showing this to you guys because it's way too complex. Let's look at Venn diagrams to try and have a more intuitive way of understanding this. Let's consider the event A and the event B. Notice that they intersect over here, and this intersection will be called A intersect B, right? If I want the probability of this whole section, the probability of the union of A and B, I have to sum the probability of A and B, but A intersect B is inside both of A and of B. So if I was to sum the probability of A and then I sum the probability of B, I would have A intersect B twice, right? So what I need to do is I have to subtract this A intersect B once so that I make sure that I have it only once in the whole probability that I am measuring. Hence, the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersect B. What if they are disjoint? Does this formula still work? It does. It does still work. If they are disjoint, let's look at it. Here's an example. I have two events that are disjoint, A and B. The probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersect B. So in this case, the probability of A, it exists, it's right here. The probability of B exists, it's right here. But what is the probability of A union intersect B? This would be 0 because A and B don't intersect. So in this case, the probability of A union B is equal to the probability of A plus the probability of B plus 0 because A and B don't intersect. And so we come across the exact same formula that we have on the fourth property of probability measures, saying that if two events are disjoint, then the probability of one or the other happening is equal to the sum of the probability of each one of them. And this general formula here that we just derived now will be very useful in the future when we have some more complex probability models to be dealing with. Okay, let's look at some examples. So let's consider the first example, where you have a sample space S that is equal to 1, 2, 3, all the way to 100. So it has events 1 to 100. And we know that the probability of 1 is equal to 0.1. Can you guys tell me what is the probability of everything 2, 3, 4, all the way to 100, but 1? So if I have all of the events, but the first one, can you tell me what the probability of that is? You can try and pause the video, try the exercise by yourself. I'll be giving the answer now. So the probability of that, well, we know that the probability of everything together is 1, right? Because the probability of S is equal to 1. And we know that the probability of 1 is equal to 0.1. So the probability of this, everything in here, the probability of 2, 3, all the way to 100 is equal to the probability of S minus the probability of 1, which is equal to 0.9. And this here is our answer for this example, right? We saw that the probability of S is equal to 1 if I have disjoint events, and I know the probability of my 1, I can just remove that and I have the probability of the rest. It comes to what we were talking at the beginning, that the probability of A, my apologies, let's go back here. We have here the probability of A, and you have the probability of A complement, and A, or anything but A, the sum of these is equal to S. And this is exactly what we have in here. We have the probability of A, let's say our probability of 1, and the probability of anything that is not 1, so 1 complement. That will be equal to 1 minus the probability of 1, which is equal to 0.9 in this case. Okay, let's consider another example. So consider the example where you have an employee that comes to work. And this employee is very bad. He always comes late or leaves early. And on each day, there is a probability that he arrives late of, let's say, 10%. And on each day, there's also the probability that he leaves early of about 20%. And there's also a probability on each day that he will both arrive late and leave early, which is equal to 5%. If we have this model, we have to be able now to put that in Venn diagrams to know how to play with these numbers. The question that I have here is, what is the probability that he either arrives late or leaves early, or both? So let's draw a Venn diagram here. And let's have this event here, where it's him arriving late. And then I have the other event where he leaves early. And in between them, we have this intersection, which is him arriving late and leaving early. And leave early. The question is, what is the probability that on any given day he will either arrive late or leave early, or both? So what is the probability of this whole thing here, everything here, all of this? So we saw that this probability, do you remember we said that the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersect B. And so let's say that A is equal to arrive late, B is equal to leaves early, and then A union B is equal to both arriving late or early, right? Both. Now we know that P of A is equal to 10%, as we mentioned up here, 10%. We know that the probability of B is equal to 20%, and the probability of A union B intersect B is equal to 5%. All of these was stated here, here, and here. And so the probability that he will either arrive late or leave early or both on any given day will be equal to 10% plus 20% minus 5%, which is equal to 25%. And this will be the answer for this example, for this problem. Let's do one last example. So consider that your soccer team is playing a game today, and that on this specific game there is a 30% chance that it wins. So let's say team on soccer game, the probability that they win is equal to 30%. Now the probability that they either win or tie, they can either win or tie, that's equal to 40%, right? Now here, this I can also write as P of win union tie, right, is equal to 40%. What is the probability, knowing all of these numbers, what is the probability of a tie? Well, again, the probability of A, the probability of win union tie is equal to the probability of win plus the probability of tie minus the probability of win intersect tie. Oh, but wait, they cannot win and tie at the same time. You either win or you have a tie. You can't have both, right? So we know that the probability of win and tie is equal to 0. Hence the probability of win union tie is equal, sorry, this is supposed to be a union tie is equal to the probability of win plus the probability of tie. And we can then isolate the probability of tie from this. If I just subtract probability of tie from here, probability of tie, I subtract the probability of win from here and the probability of win from here, and we have the probability of win union tie minus the probability of win is equal to the probability of a tie. And so, as we saw from the numbers up here, the probability of win is 30%. The probability of win union tie is 40%. So we have 40% minus 30% is equal to the probability of a tie. And this then will be equal to 10%. So there is a 10% chance that the game will be a tie on that day. Let's stop here. This was enough for today. If you have any questions, please make sure to leave them in the comments, and I will make sure to answer anything that was not clear in today's lecture. If you have suggestions, anything else that you want to learn, let me know as well. I'll be happy to talk about anything with you guys. Thank you. Have a